Hi, we're going to now look at part 2 of work where we talk about what you can do at work. So a force can make things accelerate, but it also can do work on an object. So now we're going to look at the next thing, and that is basically if you do work, you use up energy. So that's kind of the note we can put up here at the top. If you do work, then you use energy. All right, and so we're basically going to start now looking at energy and how it's related. So the first thing we want to take into consideration is that work makes things move. So the first energy we have is kinetic energy. All right, so we're going to be looking at kinetic energy. And what starts us off with this is this little idea that work can make you mad. All right, and so we're going to go through a formula derivative here to show how we can come from work to the kinetic energy formula. All right. So what we can say is that the work done on an object is that when a force acts over some distance. All right. And then what's the equation for force? Work is mass times acceleration times distance. So we get this idea, work can make you mad. Now, if we're taking this distance in the x direction, we can now take work to the max level, if you will. So work is force times distance. Force is mass times acceleration. So we like to say work will make you mad. And if you're in the x direction, you can take work to a max. Now this a times x is important. So we go over and we look at another equation that we used earlier in the year. And that is the final velocity squared equals the initial velocity squared plus twice the acceleration times the distance it travels, rx. So now we see this ax again, okay? So what we can do is we can solve this expression for ax and then substitute. So we're going to subtract vi squared from both sides, and we get the final velocity squared minus the initial velocity squared equals 2ax. So again, we want to solve for ax, so we're going to divide both sides by 2. And we get a times x equals the final velocity squared minus the initial velocity squared over 2. So now what we want to do is we want to substitute this ax into this ax, okay? So we're going to substitute, and we're going to find that the work done is equal to the mass of an object times the final velocity squared minus the initial velocity squared, all divided by 2. So we have this here. We can distribute this through, and let's get this fraction out of this 2 out of the denominator, okay? So now we can write this as work equals mass times 1/2 vf squared minus 1/2 vi squared. Now we'll distribute the m, and we'll say the work done on an object is 1/2 the mass times the velocity squared minus 1/2 the mass times the initial velocity squared. So this formula we've just found is the work done on an object that makes things move produces kinetic energy. Kinetic energy is the energy of motion. And what is the formula for kinetic energy? Well, we've just found that equation right now. All right, so the way we like to write this is we like to say that when Vi equals 0, or when it comes to a rest, when Vf equals 0, then this expression would go away, and we can say that the kinetic energy on an object is equal to 1/2 mass velocity squared. So this is our formula for kinetic energy. And we've been able to, derive that formula there using our equation. So we go back through that quickly. We say work makes you mad because force is mass times acceleration. If you're moving displacement in the x direction, you say we take work to the max. Taking an earlier expression that deals with motion, we can solve it for a sub x, and we get this expression. Substitute in, go through some algebra, and when the initial velocity is 0, we find work, or kinetic energy, equals 1/2 mv squared. So this that we have just solved for is called the work energy theorem. The work done on an object is equal to the change in kinetic energy, equal to how much the kinetic energy changes. And so we could write that as work equals the kinetic energy final minus the kinetic energy initial, which we could then substitute this formula back into and say, that the work done is 1/2 the mass final velocity squared minus 1/2 the mass initial velocity squared. So we end up right back where we came from. The work energy theorem. Solve for the amount of work it takes to make a car speed up or slow down. Solve for the amount of energy of a car. So again, either one of these is equal to each other. So this brings us to two important factors for kinetic energy that we need to look at, okay? And the first factor for kinetic energy is mass, and then the second is velocity. So they have a little bit of difference. So if you double the mass, so if you look at the formula, 1/2 mass velocity squared. If you double the mass, if I double m, I would just simply get 2 times the energy. 2 times the energy, because there's nothing there's no exponent or anything with the mass. But guess what would happen if I double the velocity? If I double this velocity, it's squared. It's an exponential relationship. An exponential relationship. So if you double the velocity, you get 2 squared, or 4 times the energy. Okay? So it's important to know that as you change the mass of an object, you get less effect in terms of energy than if you change the velocity. So what? So if the work equals the change in kinetic energy, then that's going to tell us something about the force and the distance that that force has to occur. So 2 times the velocity squared is going to produce 4 times the energy. And that means it would take 4 times the distance, or 4 times the force to create a change. So that's important. So say, for example, if you were going 20 miles per hour versus 40 miles per hour, 20 miles per hour would either take you 20 to 40. So 40 would take you 4 times the distance or stop, or 4 times the force to stop. So this is an important scenario here that we're looking at. Okay? All right, so we'll just simply take a moment now to solve a quick kinetic energy expression. All right? So say, for example, we have, a car at 50 meters per second with mass of, I don't know, 1,200 kilograms. Okay? What is kinetic energy? Well, that would be easy. The kinetic energy would be 1/2 mass velocity squared. So we'll just put that in. So we would just go 1/2, 1,200 kilograms, times the velocity, meters per second. Don't forget to square it. So we would just go, clear that out. We'll go 50 squared times 1,200 equals, and times 0.5 for 1/2. And we get this larger number. I should have used smaller numbers, but that's all right. We get 1, 5, and let's count those decimals there. We got 1, 2, 3, 4, 5, 6. So we're going to go 1.5 times 10 to the 6, and that would be joules of energy. Now, here's the idea with this. Remember, we just said that if you're doing work, you're going to use up energy. So let's say this car is moving 50 meters per second. And sometime later, now the car is at rest. So now the velocity equals 0. All right, so what's our kinetic energy at this point? Well, if it's not moving, the kinetic energy of the car equals 0. So, according to the work energy theorem, it took work to make the car go from 1.5 times 10 to the 6 joules to 0 joules sometime later, right? So it took some work to make it go from this amount of energy to this energy, to make it go from 50 meters per second to 0 meters per second. Now, what was the work? The work was done by friction of the brakes. That's what we're going to guess it's done. And so the force times the distance equals how much it has changed. Of course, 1.5 times 10 to the 6 joules minus 0 is 1.5 times 10 to the 6 joules. So at this point, we can use another number. We can decide how much force it would take to stop the car or how far the car would travel. So I guess we can just go ahead and make up a number here and go. The car is at rest after, 200 Newton friction, or the brakes were applied. So if it takes 200 newtons, how far would the car travel with this change in energy? So this is how we would use the work kinetic energy theorem, where the work done equals the change in kinetic energy. So you see we had a certain amount of energy. We now have a new amount of energy. We subtract those, and then we set it equal to work. And so this expression, we just divide by 200, and we get the distance equals, so we're going to divide this by 200, and we get 7,500 meters. So it's not very much braking force. Okay, we get 7,500 meters, not very much braking force. And since you have a lot of energy with a little bit of force, that means the distance is going to greatly increase. So quickly in review, if you do work, you use up energy. And since things are moving, the type of energy we're talking about is kinetic energy. That's the energy of motion. So we can build that formula by thinking about this idea that work makes you mad. So force is mass times acceleration times the distance. Work makes you mad. If it's in the x direction, we say a work will max out. Now, if we go through an earlier expression we used, solve for a sub x, substitute that equation in, we build our formula for kinetic energy, which is 1/2 mass times velocity squared. This is called the kinetic energy theorem, or excuse me, the work energy theorem. The amount of work done equals the change in kinetic energy. Two factors that affect kinetic energy that we need to be paying special attention to is mass and velocity. If you double the mass, you simply get 2 times the energy. If you double the velocity, 2 squared would be 4 times the energy. The velocity is an exponential relationship, so take key to pay attention to that. So basically what we're saying is, if you double the velocity of an object, 2 squared would become 4 times the energy, which means it's going to take 4 times the distance or 4 times the force to stop. So 20 miles per hour compared to 40, a 40 mile per hour car would take 4 times the distance or 4 times the force. And so here we worked just a simple example of kinetic energy. And of course, we could manipulate this formula around to solve for v squared or to solve for mass. In this case, we just solve for kinetic energy. Then I gave you an example of where the kinetic energy has changed and how we could use the change to solve for the work or the distance or maybe even the force that a car tries. So this time you're going to work some kinetic energy and work energy theorem problems.